Okay, so now let's take a look at what happens at infinite applications of this so-called X2 Whirlpool map on a quadrilateral, ABCD, some generic quadrilateral, right? So what I'm showing here is chosen the parting point 0, and in dashed green, in dashed red and dashed green, I'm showing the uh, counterclockwise red succession of points and clockwise succession of points. Okay, so let's see how the red succession of points is computed. Starting from a generic point 0 or P0, I'm going to take a first side of the quadrilateral, say side AB, and I'm going to draw a triangle. Now this triangle is going to take the two endpoints of the side and the chosen point 0 as its apex. And I'm going to compute its centroid. I'm going to mark off the centroid of AB0 with number 1 over there. So that's my first point in the sequence. Then I'm going to proceed to the second side of ABCD, which is BC. Let's do that. So I'm going to go ahead and use BC as the base for the triangle and the last computed centroid as its apex, thus obtaining point 2 in the sequence. And then I'm going to repeat it to point 3, which is over here, right? Let's just see if that's the case. I'm going to repeat that. I'm going to take the third side, which is CD, use the second computed centroid as its apex, and then that's going to give me a centroid over here at point 3, which is not marked. Okay, so as you can see, I'm proceeding from AB to BC to CD and then to DA, and then around in a whirlpool pattern around the sides of this polygon. And what I'm going to be obtaining is the red polyline. Now, as it turns out, I'm only doing 16 iterations of this map here, but you should proceed to infinity. In the end, you get the saying that it's shown approximately here, okay? These 4 red dots, they delimit a limit cycle of this map, or a limit polygon, limit quadrilateral in this case. And what we found out, surprisingly, is that this red quadrilateral is always a parallelogram, independent of ABCD. First of all, it's independent of the starting point, right? So the starting point does not affect the red quadrilateral. Okay? Secondly, it's always a parallelogram. Now, the specific parallelogram is governed by the ABCD that you choose, but the red quadrilateral is always a parallelogram. Okay? And most surprisingly, the ratio of the areas of the outer polygon by the terminal polygon is always this magical number 5. So this red polygon has 1/5 of the area of ABCD. Now the green line is doing the same as the red line, but in counterclockwise direction. So I possibly am starting here with side AD. I'm just sort of eyeballing this. Let's just check if this is the case. I'm starting with side AD, and then I'm using 0 as the apex, and point 1 over here is more than likely the centroid of AD0, right? So if I want to compute now point 2, and I'm going to proceed now in clockwise whirlpool direction, then I can do the next side here in the clockwise order is DC, so I'm going to say DC, take the last computed centroid as its apex, and then get to 2, which is the centroid of this new triangle, and so forth and so on in a clockwise fashion, right? So I have 2 progressions here. I have 2 sequences. The counterclockwise one, and when I say counterclockwise, I'm talking about the way you traverse the sides of this polygon. That gives me the red limit cycle, which, as we said, is 1/5 of the area, and it's a parallelogram. And if you do the clockwise progression, you also get a green parallelogram, also at 1/5 of the area of ABCD, but rotated with respect to the red one, right? Interestingly, the 8 vertices of these 2 parallelograms fall on an ellipse. The center of the ellipse, C0, is the average of ABCD. Okay, so there's a lot of harmony here, and as I move around, for example, I can make this guy be self-intersecting. Let's try to make a self-intersecting example here, like so. Okay, you can see here that the area, there's a numerical approximation. You still get the 2 red-green parallelograms. Let's move 0 around, And let's make this be maybe a bit more visible, like that. So you still get a red limit cycle, which is a parallelogram at 1/5 of the area, and you still get a green, and the vertices are still on an ellipse, and the center of this ellipse coincides with the average of ABCD. Okay, so we thought this was pretty cool. We have worked out a proof that is based on a surprising fact here, and this is kind of, you know, you cannot use the same affine argument that we used for the n equals 3 case that basically was had an equilateral affine preimage, and everything. It sufficed to analyze the problem on the affine equilateral affine preimage. Here you don't have an affine preimage that is regular, but there's another property that we're going to talk about in a future video that allows us to prove this property of constant area ratio irrespective of ABCD in a pretty elegant way. Okay, so here are a few other examples, right? And I can move 0 around, and that doesn't affect the position of the limit parallelograms. Okay, anyway, I'll see you on the next video.